Thank you.
And we're going.
All right, excellent. Hi, so I'm Alex Rassin. I forgot the microphone. All right, let's try it again. I'm Alex Rassin. I'm assistant professor at DePaul University. So me and several people from my research lab are very excited to be here. Thank you for having us. And I want to talk about forensic applications and database carving for that purpose. So the lab has a lot of people, and I don't have some of the pictures, but this is the group who pretty much leads the effort. And it's mostly DePaul lab, except Jonathan Greer, who's the principal of Greer Forensics, and he provides us with some real-world motivation. His expertise is in data theft and similar work. So why have we bothered doing this? So obviously forensics is interesting, but specifically we were motivated by data access, data theft, data tampering potentially. And every day you pretty much see something in the news, someone stole a bunch of accounts, a bunch of data. And even more interesting is that oftentimes it takes forever until someone notices. And even if you notice the data may have been stolen, you still have no good way of proving it necessarily. And this is one of the very important aspects. It's not just about detecting data theft, it's also often being able to verify somehow, especially if you're dealing with internal hacking. And there is also a lot of interest from perspective of doing mobile device analysis, because it turns out that every time you need to store something on a mobile device, you pretty much use SQLite, which is a lightweight relational database, and it's easier to do that than to reinvent the wheel. And so you may not think about this, but databases are in fact everywhere. So every phone, Android, iPhones, browser bookmarks would often live in SQLite database, and obviously any website, anything that has a front end and a back end, somewhere on the back end there's a database. Often relational, sometimes something else. And primarily our focus is on the relational databases, but we plan to expand. So the goals kind of broadly are to get back things that were deleted, because once you delete something from database perspective, it stops existing. But there is obviously a lot of forensic value and a lot of interest in seeing things that were in the system before, but were deleted. To see who's doing what on the system, to detect what's being changed, to detect what operations are happening or what operations almost happened. And a lot of it you can see. We're also looking into data tampering, especially from the inside. So we have a paper that's that was just accepted to DFRWS. And there we look at what happens if the tampering is happening from the inside. So it's very easy for a database administrator to make changes that were not intended because they have sufficient control. And so the whole idea of doing this kind of analysis is that you don't trust anyone. You don't trust the system, you don't trust the logs, you just look at the storage and you see what's happening. So first, as a little detour, this is all the possible components of a database. So logs, either audit or write-ahead logs are for transaction integrity. You may care about what's happening in RAM. You may care about actual data. And then there's all the unqueryable stuff. So for example, indexes, and I have some pictures, would be helpful in accessing data faster. They're not technically data. They're actually auxiliary data, which is something you use to get to the data you want. But obviously, there are things you could see in them. In fact, sometimes more than in actual raw data. And if you're thinking database recovery or database access, which is what a lot of people were thinking, especially when we started this work, then it turns out that database recovery only cares about the tangible stuff. So if you have something in a database table, then the recovery would try to make sure that you can get it back. But if you deleted the record, or if you cared about what was in the cache, well, that's not really something that's being guarded by any of the systems. So generally you can't get it back, and this is actually done by design. So relational databases were intentionally built to take control over storage, and that's part of the reason, as you'll see, why analysis is so much fun, because it's this own little world, and you get your logical interface, and the database handles everything internally. And oftentimes you can't tell, and that is intentional, but sometimes you want to. And then there's one more kind of interesting aspect of getting this data. So suppose that the database did give you back what you asked for. Problem is, how would you actually verify that it's accurate and hasn't actually changed between the time you asked for it and the time it got back to you? Because obviously, database querying is not really built to guarantee a chain of custody, that data was not affected, and you are on the way. So you also want a mechanism that gives you exactly what's there and guarantees that nothing quietly changed. Because again, you have no control over what happens in the storage. So you don't know what actually will happen when you pull data out. So again, as a little detour, in general, I'm sure most of you are familiar with this. If you delete a file in a file system, anything at all, nothing actually gets wiped out for many reasons, partially because no one wants to do any work. So it's easier to say, this is just unallocated space, and I'll get back to you later. If I need to write something, then I can use this location to actually store something. And then over time, deleted data would actually get overwritten and disappear with some unknown duration. And so then the process of file carving, which is a well-respected technique in file systems and digital forensics, is to look through the disk storage, ignoring the file system, because sometimes you're looking for things that are gone or corrupted. And then look for a magic sequence of characters that indicate that this looks like a JPEG, or this looks like a PDF, or a Word file. And then you say, well, if I were to assume that it starts here, and this is the header of the file, then I can scan through and pull it out. And this is how all of the file carving tools work. It gets a little more interesting. For example, if you have an image embedded in Microsoft Word document, you might still be able to get it out, or it might look different. That's the basic idea. And the viewer is a little skewed, but I think you get the idea of fragmentation right here. So you look through the disk, you find the header of a file. If it's an image, then you start reading through multiple fragments, you put them together, and voila, you have the file. Now again, this gets somewhat more interesting if the file happens to be fragmented on disk. So half of the file is here, half of the file is there. You get first half of the image. This is from one of the papers that we're talking about putting together, back together the puzzle. That's effectively what you have to do. You put together different little pieces and you try to assemble them back into a coherent file. So this is what file carving is. This is something that's been done for at least a decade, if not longer. It turns out that file carving doesn't really help you with a database. Specifically, database files, because databases are their own little universe, database files do not have file headers. Actually, relational database files consist of a bunch of independent and mostly self-contained pages. So if you look through, you don't find the header of a file and the end of a file. You just find some sequence of pages that constitute different structures in the database. And interpreting them is even more complicated, which is what I'd like to argue. So once you found the page or a content, it's not that easy to tell what you're looking at, because again, it wasn't really made for external consumption. It's pretty much internal storage. So again, as a little detour. So from database perspective, you look at something and you have a table. In this case, I have a table, 4 columns, 6 rows, that contains user IDs, names, positions, and hometowns. So from logical perspective, if you were to query the database, you ask for some columns, you ask for some data, and that's what you can request. It is by design that you have no way of telling how it's being stored. Typically, in row-based relational databases, which are the majority of relational databases, in reality, the data is separated into pages. So, for example, the first 2 rows might live on page 1, and then 2 more rows might live on page 2. And this is what it looks like. Each page is a little self-contained semi-file, and this is what you find in storage. But it gets more interesting when you look at other structures. So in addition to the table that we had before, you might also have an index. An index is simply a value to location pointer that helps you find your data. So in this case, I have an index on hometown, which tells you if I'm looking for a particular town, which row do I find it in? Again, this is auxiliary structures because it's not part of the data. It's a copy of the data that's created to help you find what you're looking for. And if you think I don't remember creating indexes, well, a lot of them get created automatically, which is also an interesting fact. So when you create a primary key, when you create a unique constraint, a database will build an index to enforce things without notifying the user, of course. And so each one of the structures also are typically stored in the pages. Indexes are a little more complicated than on this picture, but ultimately it's a big structure that's fragmented into individual pages and somehow stored on disk. And pages would often try to align with file system pages, or at least similar. So a page at a very, very high level of view contains maybe 15–20% various header data. So each page has its own header that, among other things, might tell you where this page belongs to, so which data structure it comes from, what's the data type, the category of a data structure. Then there is a row directory, which is just a bunch of pointers to the actual rows. And then somewhere inside the page in the payload component, there are the actual data rows with possibly some additional metadata. So the interesting part about all of this is that a lot of the details vary database to database, but every relational database we've tested, of which there is at least 8 to 10, they all have the same general structure. And the first thing we've set out to do was to come up with a set of descriptive parameters that'll tell you how exactly are things set up. So generally it looks like this, and then some details as to what's on top, what's on the bottom, how many metadata entries you have. That varies from system to system. And so once you step back and actually look at the storage as a big collection of database pages, then you can begin to interpret what the storage contains and try to understand what you can learn from it. So we built this tool, dbcarver, as a reference to file carving process. And it consists of two different pieces, the parameter detector and the actual data parsing step. And I'll talk about each one separately. So first, parameter detector. Again, remember, every page looks similarly, but the details vary from system to system. And wouldn't it be nice to be able to learn what the system actually does? So what parameter detector does, you install a database, then it automatically loads a bunch of synthetic data that we know what it looks like. And then by capturing storage, it can deduce how the data lands in the database storage. So it can pretty much learn the layout of a database. And one of the reasons we wanted this is to be able to check what happens with a new version. And typically things don't change. But for example, at least some time ago, maybe 10 years ago, Postgres had actually made a significant switch where several of the parameters were changed. Although normally you wouldn't really tweak it too much because it requires significant changes in processing. So obviously there's a lot of parameters. I'll mention a couple. For example, and this, by the way, is the list of databases we primarily focus on. A couple more are not mentioned here because they happen to share the same storage. So for example, MariaDB uses the storage engine of MySQL. Greenplum uses the storage engine of Postgres. So the pages are more or less the same. Of course, the engine itself is a little different. So for example, the page might have a structure identifier that tells you what kind of structure the page belongs to. Or sometimes it might not be on the page. Similarly, as I mentioned, sometimes you insert rows from the bottom to top, stacking them. Sometimes you start from the top and down the bottom. This is the kind of thing that different databases choose different strategies. Now, the more interesting parameters are the row identifier and column count, which interact in good ways. So row identifier is this extra column that the database may or may not choose to create. So normally, let's say in this example, I have 3 columns, number, name, and city. Sometimes you'd actually see those 3 values. Sometimes there is a fourth column, which is the internal row ID. It's called CTID in Postgres, row ID in Oracle. So you can actually query for it. And in reality, on the physical page, there's more columns than you've created. And then some databases choose to keep track of how many columns there are by just having the number of columns stored on the page. And then the interesting interaction part is that that count sometimes does include the fake column and sometimes does not. So you can have all sorts of combination. You might have a row ID, you might have a count of 3, you might have a count of 4, or you might have neither. And all of this is a possibility system to system. So then there is the value deconstruction, which is also a kind of database to database thing. So in Postgres, things are pretty obvious. For example, for numbers, you just have a 256, 4 bytes fixed storage, and the numbers interpreted this way. And then there's Oracle. I firmly believe that Oracle chose this design simply to have something for us to talk about. So if you think about how they represent the numbers, 1 digit is there to tell you how many digits a number contains. So the first 3 numbers, it starts from 3 because there's only 3 rather than 4 bytes being used. Then the second one refers to how many zeros there are at the end. So 192 means no zeros, 193 means 2 zeros, and so on. And then the final number in the first example is the value itself minus plus 1. So 4 is represented as 3 for 3 numbers, 192 no zeros, 5 for 4. Then 40 is represented as 3, 192, and 41. And then 400 is represented as 3, 193 for 2 zeros, and then 5 for the 4 in the beginning. And then finally I have, so this is 4 bytes, then 193 for 2 zeros, then 5 for 400, and then 41 for 40. Those are the actual 4 bytes that you'd see in the storage. And I have a couple more examples, and I have no idea how my PhD student figured it out. Still not sure, but somehow he learned it. And it works, so clearly it is actually how things are stored. So one more interesting example that's still kind of something we're working on. We have some heuristics, but it's still work in progress. So if you have a string, the typical mechanism is to have a length of a string followed by the actual data. Now, if you happen to have a 3-character string, then it might be difficult to tell which one you're looking at because both are valid interpretations. One says this is a 3 and this is a 3-character JAY. The other possibility is to interpret that as a number of 4 bytes. And it's not necessarily obvious because at least individual pages don't explicitly store that information. You might find it somewhere else, of course. So then there's parsing. I'll also give a couple examples. Just to give you a quick example of getting stuff out of Postgres and some more very curious algebraic decisions. So some more parameters. The orange raw data delimiter is where the individual row begins on a page. Somewhere above there is a header. This is just a piece of a page, byte by byte, starting where the rows are. And the 2 columns you're seeing here, this is the ASCII character manifestation, and this is the decimal value, and obviously some are not visible ASCII characters. So the 3 bytes in orange indicate that the data begins here. Then there's another parameter that tells you how far you go where the row actually starts. Then you have a 4-byte number, and the 4-byte number in Postgres is stored in a at least relatively obvious way. Then you have a string length, but it would be too simple to store the actual string length. So what in fact happens, you have 39 that represents 18. And how do you learn that? Well, there are 2 parameters, one of which you subtract and the other one of which you divide by. For Postgres in particular, it's -3 divided by 2, which gives you the actual length of a string that the database means. So when it says 39, it's an 18-byte string. Again, not quite sure how he figured it out, but there you have it. So again, this is back to our example of what the value might contain. So 65,000 is 4 for 4 bytes, 195 for the zeros, 7 for the 6 in the beginning, and then 51 for the 50 in 65,000. And there's a lot of other interesting issues. So we kind of have a handle on internal row IDs, but databases might also have binary large objects, which could be, once again, images or some other data types. Some databases use compression. Sometimes compression kicks in automatically, like in Postgres. Obviously, there's encryption issues. So deconstruction of values is still somewhat of a work in progress. And then I wanted to show some examples of the kind of things you can learn from various operations. So again, because when you issue a delete or an update or any sort of command, things do not immediately happen. The change is very indirect. So for example, if I say delete a row, then the row is marked as deleted but remains there. And the curious result is that the attacker or someone using our tool then has more access to the data, because as the user with legitimate access, you can't really have a deleted row because it's been deleted. But it's still there. It's simply marked as deleted. And then if you have an update, especially if you have an update to a larger value, so in this case changing Smith to not Smith, you can't fit the original value where the old value used to be, so you have to delete the old one, like you do normally, and then reinsert a new one. So pretty much everything stays around for an indefinite amount of time. And here's an example of an actual data. So this is from SQLite, from an Android device that came off eBay, and one of our collaborators got us. And this is a single page that happens to contain SMS messages. So this page address tells you where the data lived on a disk. A record count, at least in this case, tells you how many active records. There's actually 21 records, 20 active, 1 deleted. So this says 20, but in reality there's 21. Those are the 21 records, and then on the bottom you have a deleted one, which has been a little bit nulled out, but it's still there, and obviously recoverable. And in this particular case, you also have a row ID, which is a column that was never created by the user. This is something that SQLite keeps for its own purposes. So that's actual data from an actual phone. One more thing I wanted to briefly give you some background on. So this is the stochastic forensics mechanism is actually something that was proposed by our collaborator, Jonathan Greer. And he had this idea and published a paper a few years ago, also in DFRWS, that it's possible to look at the side effects created by the system, not things related to security, but actions performed by the system for some other purpose to learn what is happening. And that's the exact same motivation we're going for here in terms of applications, to look at the storage or to look at the system behavior and to learn what is happening, not because there is a security mechanism that tells us, that logs things, but because this is what happens when you do X. When you do X, Y happens, so the storage reflects it. It's actually much harder to avoid than the security logging, because with enough privileges you can change that. And to give you an idea of how the motivated approach works, so what he did back then was to look at Windows file system timestamps. So every time you access a file in Windows, there is a timestamp that is being changed. So if you look at the folder, and his specific task was to prove that an employee had absconded with some data before departing. So if you look at the folder and you look at the timestamps, on the bottom in green is the typical distribution of the timestamps, where some things were changed recently, some things were changed longer ago, some were changed a while ago, and some dates go all the way back to 0 or something unset. So if you happen to copy a folder at some point, then you recursively go through the whole folder and you touch every file. That's how folder copy works. So that tends to create a cutoff right here, which is a very likely proof, and there is some more analysis in the paper that tells how likely it is, which is a proof that at this moment where you see the red spike, a cutoff, someone had copied the whole folder, and that it doesn't have the normal pattern distribution of timestamps. And of course, the interesting thing about it is that this is not a security mechanism. This is just something that the system does anyway for some other reasons. So to give some more idea of the kind of stuff you can see in storage, again, remember table on the right, index on the left. So if you update something, the old value is deleted, the new value is inserted, and then of course index and other structures would keep their own copy. So the old value is there and the new value is there, and nothing changes. And one more thing about caching, in case to remind you how at least database caching works. So if you have data on disk on the left, you access a couple of pages or change a couple of pages, the copy is loaded into memory, changed in memory, and for a while it actually differs from what's on disk. Then as you access more stuff, like for example another query accesses page D, that goes into memory, and then the old stuff has to be flushed out and synchronized back to disk. So now, just to go through the same steps in a database, and those are all different moments in time you can capture if you look at the storage, depending on when you look at the system or where you are in this process of an update. So again, I start with the data, I issue an update. First thing that has to happen is data goes into memory. Second, it gets modified in memory, and same applies to an index, by the way. Index also gets loaded into memory because you can't alter things on disk. And then at this point you can see the difference, and you can essentially see anything in progress because cache doesn't match to disk. Then at some point the data might be written back to disk and remain in memory, and then eventually it would be flushed out. So I'll skip over most of it because of our setup issues. I'll just show you a quick summary of this. So this is Oracle buffer cache, 50,000 pages. Each page is a pixel. So this is 50,000 pixels. And what we're simply showing is you start with a preloaded cache of some unrelated data, and then you start running queries, and then the old contents of memory start being overwritten step by step. So first there is some red stuff on the bottom, then there's more green things coming from line order and another synthetic table. And it's kind of first in, first out, sequential overwrite. And you can also, don't know if you can see it here, but I can show you the bigger version. You can also see specs of the old stuff. So it's not necessarily completely overwritten, at least not until multiple passes. Those are all the things you can see in storage. All right, so the delete example is definitely one of my favorites because it again shows the difference between the command you issue and what actually happens in the system, and things that you can't necessarily see as the user or understand. So let's say you decide to delete a row in a database, and this particular row lives in a table, and there is an index, and there is a materialist view that stores this information as well. Phone number, social security number, doesn't matter. And as I mentioned, indexes could come into existence for many reasons. It's sufficient to have a unique constraint that automatically creates an index. So you might think that you issue delete and data gets deleted, or at least that maybe you issue delete command and data gets marked and then later purged. However, that's not what actually happens. So we're tracking multiple steps in a timeline. Initially you load the data, then you issue delete at time 1. At time 2 you refresh the materialist view. At time 3 you flush out the contents of the memory. And at time 4 you run enough query to overwrite the memory. And then at time 5 you issue a bunch of other rebuilds, rebuilding the entire structure. So let me talk about what actually happens when you issue delete. So here we are, we start with 3 different values. This is the value in table, this is the value in the index, this is the materialist view. When you issue delete, first thing that happens, 2 more values get created. Nothing on disk gets touched at all. The index page gets loaded as part of finding the value because you need to find it to delete it. And then the table page gets loaded into memory, and then in memory it gets marked as deleted. So you've gone up to 5, one of which is marked as deleted instead of 3. That's the immediate reaction. Then you perform a refresh, that brings you up to 6, because the materialist view gets a copy of a page that has a value marked as deleted. Still different from disk, you've now doubled the number of values by issuing the delete. There is now 6 instances instead of 3. Then you issue the flush command, which doesn't actually remove anything from memory. It simply forces the memory to synchronize with disk. So at T3, those two values also get marked as deleted to match the memory. The values in memory are still there. They're simply considered free space. And you still have 6 values, and there's all sorts of colorful markups, some deleted, some not. So it takes a very, very, very long time for a value to actually go away. So you would need to rebuild, you would need to run enough queries to free out memory, which is time 4. And then you would need to rebuild the structures one way or another, because otherwise it'll pretty much stay for some time. All right, so a couple more examples, and then we'll have some time for questions. So this is more recent work. Again, the idea is you look at the storage, you look at the log, and you say something doesn't match. You don't know why necessarily, but you know that either a particularly clever database administrator or a hacker with too much access has managed to do something that has not been reflected in the log. Right? The system has been compromised, and once the system's compromised, if the database hasn't logged it, then there's really no chance that it's going to protect you from this attack, because it doesn't even know that something's wrong. So in this particular example, we have a log file with 2 deletes. One says delete entries for Chicago, one says delete entries that start from Chris. And then what you can do is, and we have some algorithms in the paper, what you can do is to match it, to say this deleted row that I see can match this delete action. So for example, Christine record 1 could have been deleted by delete Chicago, could have been deleted by this. You don't necessarily know. And then the entry for Christopher could have been deleted only by this, but it matches. And then record number 4, there is no explaining how it got deleted. So really the only explanation is someone did something without logging, by accident or on purpose, but the point is something doesn't match, and the audit wouldn't help you, because the log has no recollection as to who actually deleted row 4. And you might think, if you database administrator is clever enough, they could find a way to overwrite the data, right? So obviously, the deleted data doesn't stay there forever. It is marked as free space, and as new stuff comes in, subject to different rules, and some, depending on the system, it'll eventually get overwritten by something new. So here's another example specifically to deal with particularly clever DBAs. So let's say you delete the record, and you had a record that said lamp in the furniture table. And then you said, well, if I just leave it there, then someone's going to find it, and I'll be found out that there's no log record for it. So you insert a new record with the value of dog right here. And depending on database, but in many cases, the value can get overwritten. However, 2 problems with that. First of all, you have to match the value to be exact size. If you insert dog over lamp, there is still the letter P right there, which you can still see in the storage, because again, nothing goes away. The first 3 characters got overwritten, but the old value is still hanging out there. And you can at least see that something used to be here, and you can see a part of the value remaining on disk. And this thing definitely won't go away for a while, because there is nothing you can insert over a little fragment of data. And then more interestingly, the index pretty much keeps things forever. So most of database indexes would never let go of a value at all until rebuilt. So in addition to this, for dog you have the record with index of 0. And then for record 3, which used to be here, you still have an entry in the index as well that points there, and then somewhere else the database determines that the value has been deleted. And for this, first of all, it almost never goes away. This has to do with how transactions work and how the indexing structures operate. And more interestingly, you can't actually override it. You can't issue direct commands against memory, and you can't say insert something into an index here. That's not, you can kind of time it for a table, but you can't really do this for an index. So if you look at everything, then it's really hard to find your way around what the storage could reveal about the database. All right, great. That leaves us some time for questions. So in general, we've been working on this database carving solutions for a while. We pretty much want to, in the long run, we want to build something that lets you ask meta queries, ask you something about the database. Even if you don't trust the database, or if database doesn't provide this kind of interface, if you want to know something that's happening on the inside, you want to be able to ask the question and to say, what is this doing? Does this match to this? What's in memory? What's being changed? Figure out anything that might be off, and no assumptions. Because most of the forensic and security approaches that you do see say, well, you have to configure your logs just so, you have to make sure that your database has this security extension, and then you can be relatively secure. But of course, in reality, you run on the systems with whatever settings you have, and you want to just be able to come in and say, what is happening here right now? So we're definitely looking for collaborations and use cases because databases are everywhere, and we're looking for more exciting applications that we could do. And we also happen to have a job opening in the lab, except that it's not directly on this topic, but more on reproducibility. However, still, if you're interested, do talk to me or to anyone from our group. And with that, I think we still have a few minutes for questions. Questions? Was that clear? Yeah.
So I missed the beginning of this, and I apologize if this is.
That's fine.
Answer or whatever, or if this is outside the scope of this. But how do you prevent evidence contamination when you're actually collecting the emission data?
Right. Well, so the question was, how do you prevent evidence contamination when you collect the data? Mostly the observation is that if you trust the system itself to answer about what's in the database, then there is zero ways of knowing if it's reliable. Now, as far as collecting it, so our best approach at the moment is to, there is still the physical chain of custody, right? You need to take an image of a drive, and you need to carry it over, and no one can tamper with the storage, and the physical control is really outside of the realm of digital forensics. However, what we can do to avoid contamination is exactly looking at the storage in read-only mode. So that's kind of the big motivation, right? Even if a database could answer things, and even if you trusted its answers, you would have to start a database. And once it runs, who knows what it does? So what we want to do is to be able to query over storage that's mounted in read-only. You could physically disable the ability to write. And we would just answer things about storage because we're just looking from the outside, independently, right? So this way, as long as you can tell me that no one changed the drive, and as long as you can physically flip the switch to not let it be modified, and then we know it hasn't changed.
So sorry, that kind of brings us to the secondary question.
Mm-hmm.
How do you validate the report? I guess you would assume that you have, let's just say you have a large client who has a server rack with 50 drives on it, right? It's not really realistic to switch off one of those drives in that rack and then just be like, okay, only this drive is what you're looking at. It's not really realistic because they'd have to shut down the whole server, right, in order for you to do your evidence collection. So is that really viable?
I see. So the question is, how practical is it to stop everything to be able to collect evidence? So obviously, again, I'm not really an actual investigator. So obviously you need to come in and capture the images. In an ideal world, someone comes in, stops the servers and images them. In the worst case scenario, they come in and take the computers. But kind of the physical capture part, I agree it's inconvenient, but in order to do any sort of forensic analysis, you would have to capture the image of all relevant storage. And I would say it's more of a physical custody issue. I think you can shut down things and image them on a separate read-only thing, and then presumably you can then leave. But yeah, so this is a good question, but that's somewhat orthogonal to the problem of performing analysis. And the same question, I'm surprised it's not a tertiary question, is what happens with encryption. And I would say it's the same answer, where you need to physically get to the data, and decrypting it is also a problem. And then interpreting what's in the database and coming up with evidence is a separate problem. And I agree, we're not really solving the total drive encryption. The only thing we have going for us is that, at least at the moment, except for most dedicated hardware, even if you have total encryption at the disk level, anytime you access something and move it into memory, that gets decrypted to be processed. So even if your whole drive is encrypted, you can see everything that shows up in memory. Yes?
Do the database manufacturers have any sorts of CRCs, hashing, integrity checking that can be used?
Used for what?
Well, I mean, they have to verify their own validity of the data in the database.
I see. Yes, excellent question. So the question is there a CRC checking? So that, interestingly enough, depends on the database. In some system, they pretty much, like in MySQL, as far as I know, you change the number of rows on a page. We've tried playing with storage tampering a little bit. You change the number of rows on a page, and it just reads fewer rows, and nothing happens. In commercial systems, you do have a checksum, meaning that if a page is changed, it realizes that fact. And at least in SQL Server and in Oracle, there are some tools that can let you fix it, but fix it to the point of ejecting the pages, not actually fixing it. One of our goals, of course, would be also to look at, can you recover or fix the data if something went wrong? Best case scenario, you would be able to cut off, in existing tools, you can cut off the pages where the checksum doesn't match. If storage shifts, then it's actually surprisingly easy to bring a database to its knees. If you change a value, you can kind of find the checksum. If you shift the addresses, that's it. It knows something is wrong, but the checksum is in the wrong place, and that's it. You just get panic messages about can't start, can't find something. So you definitely, tampering with storage is definitely effective. All right, thank you. Thank you very much. All right, this is not my computer. So. All right, have fun. Well,
how's the mic? It looks like it's pretty bouncy.
The mic is okay, I think, as long as you hold it.
Okay, so that's just the whole
yeah, I tried to align it with me, and then I forgot about it and I walked away.
So, yeah, you have a computer?
Yep.
Mac?